Hi, my name is Vishwak, and I'll be presenting our work on large-scale pre-training for visual dialogue. The visual dialogue task is the following. Given an image, a natural language dialogue history consisting of a sequence of question-answer pairs, and a follow-up question, the model has to generate a free-form natural language answer. The VisDial dataset is a large-scale dataset for this task, consisting of human-to-human dialogues on around 120,000 images from Coco, sourced from Amazon Mechanical Turk. For evaluation, there are 100 answer options for each follow-up question, consisting of nearest neighbors, popular and random answers from the dataset, along with the ground truth answer provided by the human. Models are to rank these 100 answer options and are evaluated on retrieval metrics such as mean rank of the ground truth answer, mean reciprocal rank, etc. Here's an example from the dataset. The caption is 3 elephants next to one another near a blue body of water. The dialogue history is as shown. The follow-up question is, are there any people? To which the ground truth answer is no. We note that some of the other answer options, including nope, not that can be seen, etc., are accurate too. A concern with the evaluation procedure described earlier is that the evaluation does not account for multiple correct answers and only considers a single ground truth answer per question. To address this, the dataset for a subset of the samples also contains dense annotations, which are fine-grained relevance scores for each answer option, thereby allowing the evaluation to account for multiple correct answers. Models are evaluated based on the NDCG metric. To summarize the metric, each question has 100 answer options, and based on the rank of the ground truth answer, we calculate the MRR, the recall at 1, 5, 10, and the mean rank. We then look at the dense relevance scores of the answer options to calculate the NDCG metric. Prior work has not leveraged a significant amount of shared abstraction and visual grounding in related tasks in vision and language such as captioning, visual question answering, etc., that can benefit visual dialogue. Related work such as BERT pre-train on language corpora such as Wikipedia and books corpus to train powerful language understanding models. Prior work such as Wilbert pre-train on vision and language corpora in addition to pre-training on language corpora and introduce co-attention layers to learn powerful cross-modal representations. This approach has led to impressive results on downstream vision and language tasks like visual question answering, image captioning, etc. We present the first large-scale pre-training approach for transformer-based models for visual dialogue by adapting Wilbert to the visual dialogue task by carefully constraining the input representations and the pre-training losses. Following Wilbert, we first pre-train on Wikipedia and books corpus datasets with the masked language modeling loss, where the model tries to predict the masked token, and we also train with the next sentence prediction loss by trying to predict whether two sentences are aligned. To create negative samples, the aligned sentence is replaced with a random sentence. We then pre-train on the Conceptual Captions dataset, which is a large-scale dataset of aligned images and captions. For the image stream, the model takes in as input various detected objects in a scene. We pre-train the model with the masked image region loss, where the model tries to predict the masked image features, and with the masked language modeling loss. Further, we use the representations of the image and CLS tokens to predict whether an image and caption are aligned. To sample negatives, we replace the caption with another caption from the dataset. We also pre-train on the VQA dataset, where similar to the conceptual captions pre-training, we transform the representations of the image and CLS tokens to predict a distribution over 3,129 answers in the VQA dataset. Following this, we fine-tune on the sparse annotations from the VisDial dataset. We do not change the input representation for the image stream compared to the conceptual captions and VQA pre-training. However, for the language stream, we do the following. We append the caption, the question-answer pairs in the dialogue history, the current question and the candidate answer, and delimit them with the sep token. We also add question embeddings to the question tokens and answer embeddings to the answer tokens to help the model understand the concept of a dialogue round. We then train the model with the masked image region loss and the masked language modeling loss, and train to predict whether the answer candidate is the right answer given the dialogue history and the image. To generate negative samples, we randomly sample other candidate answers. We then optionally fine-tune on dense annotations. We first normalize the relevance scores for all the answer options. We then predict the scores for all the candidate answers. We then normalize the model predictions and train on the cross-entropy loss between the distribution defined by the relevance scores and the distribution defined by the model predictions. Given these training strategies, we train the following variants. We first pre-train on the conceptual captions dataset and the VQA datasets, and then fine-tune on sparse annotations from VisStyle. We call this our base model. We also train a variant where we just pre-train on the conceptual captions dataset and fine-tune on sparse annotations from VisStyle. This variant helps us understand the importance of training on the VQA dataset, as the visual question answering task is similar to the visual dialog task, and images for both the VQA and VisDial datasets are sourced from COCO. We also train a variant where we remove the vision stream and the co-attention layers and fine-tune the language stream with sparse annotations from VisDial. We then introduce the vision stream and the co-attention layers and fine-tune the entire model on the sparse annotations. This variant helps us put gains coming from vision and language pre-training in perspective. We also train a variant where we follow the training routine from our base model and pre-train on the conceptual captions and VQA datasets, and then fine-tune on sparse annotations from VisDial. We then fine-tune on the dense annotations from VisDial, and we refer to this variant as CE as we train on the cross-entropy loss between the dense relevance scores and the model predictions. We first note that our base model, pre-trained on both the conceptual captions and VQ datasets, does significantly better than the variant just pre-trained on conceptual captions. Therefore, training on VQA helps significantly. We also see that the base model performs much better than the model without vision and language pre-training, thus showing that pre-training on vision and language datasets helps significantly. Let us now look at results from the test split. We know that our base model gets a state-of-the-art single model results on the VisDial task on all the sparse metrics, just MRR, recall at 1, 5, 10, and mean rank. And our model fine-tuned on dense annotations gets state-of-the-art single model results on NDCG. Compared to the base model, training on dense annotations leads to a very high NDCG but very low MRR. We investigate this further and find that this is due to a misalignment between dense annotations and sparse annotations. We look at the trend between the mean rank of the ground truth answers, lower is better, and the relevance score, and find that the model fine-tuned on dense annotations does significantly worse when the relevance score of the ground truth answers are low. Further, we find that around 50% of sparse annotations have a relevance score of less than 0.8, which is surprising as you would expected all the sparse annotations to have a high relevance score. The following plot of the top 50 relevant answers also shows us that most of the relevant answers have a bias to binary answers such as yes, no, no, I don't, etc., and a bias towards safe, uninformative answers such as I do not see any, etc. Let us now look at a couple of qualitative samples. We make a few observations. The first observation is that the base model is surprisingly accurate. For example, for the question, can you see any people, the predicted answer is part of a person. And for the question, anything else interesting about the photo, the predicted answer is the dog is looking up at the person with his tongue out. The second observation is that the CE model often answers with generic responses such as I cannot tell, especially for questions involving some amount of subjectivity and uncertainty. For example, what color is the chair? The predicted answer is I cannot tell. The chair seems to be in the shadow in the image. And for the question, does the dog look happy? The predicted answer is I can't tell. The final observation we make is that this also highlights a consequence of the misalignment between ground truth and dense annotations. While the ground truth answer provides one reasonable response to the question asked, it is answer specific to quite an extent, and there may be other correct answers annotated in the dense annotations. In conclusion, we introduced the first large-scale pre-training approach for transformer-based models for visual dialogue, leading to state-of-the-art single model results. We also find that the NDCG and MRR metrics do not correlate well with each other, and we carefully analyze this finding. Thanks for tuning in. We have attached links to the paper and our code repository. Please feel free to reach out to us. Thank you.